So today I'll just prove the general McDonald eta function identity, more or less following the same prototype that we did for SL2. So there is no surprises. So, there are no surprises till the very end, I should say. So there's something that's nice sort of pops out at the end. But anyway, so recall from last time that the McDonald eta function identity was essentially built on the wild character formula, which contrary to what you have heard yesterday is beautiful, useful, maybe not in sharp peak, but so. Okay, so so I'm going to write just the wild denominator identity, which says that this alternating sum minus rho minus w rho minus rho is the product. Okay, and now my setting is as usual. I should say we are talking about G is a fine Katsuri algebra, which is, and there is as usual a underlying finite dimensional simply algebra G dot or G naught. Okay, and this is the denominator identity for this affine the algebra D. Okay, now what we did in the case of SL2 was to just unravel the sum on the product sides. So the product is always the easier side, because here we actually know what all the positive roots look like and we know what their multiplicities are. Okay, so let's do that now again in this general situation. So let's look at the product side of the identity. So to do this, I should recall what the positive roots look like. So we said last time they are sort of in three different types. There's either alpha plus n minus 1 delta, where alpha is a positive root of the underlying affine and n is at least 1. Right? It's just another way of saying it's alpha plus n delta for n at least 0, right, if alpha is already positive, or if alpha is negative, or meaning to say I'll think of it as minus alpha, I should start from n at least 1 and then finally the imaginary roots n delta. Okay, so there are three classes of, the real and the imaginary roots. The real we will split further into these two types, right? So this is the general situation. And so let's just plug all of these in. We'll also recall that the multiplicities are 1, multiplicities of all these roots, the real roots are 1 and the imaginary roots have multiplicity L, which is the rank of the underlying Lie algebra, meaning to say it's a dimension of the finite dimensional Cartan algebra. Okay, and that we saw comes from the way the corresponding root space was constructed. It's just H naught tensor t to the n. Okay, so we are ready to plug in. So the product side, just call it P, is now product. So let's run it over all alpha, okay, I guess over all n at least 1. So first I have the term 1 minus e to the minus n delta to the L. So that would just be the imaginary terms. Then I would also have a product. So there is now further product over all alphas, delta naught plus. Okay, so now I should have 1 minus e to the, let's see, what should it be? So I should look at these ones. So I should have e to the minus of these guys. So e to the minus alpha minus n minus 1 delta. Then I should also have e to the plus alpha minus n delta. It's fine. Just put them all together. And like we did last time, remember we sort of renamed the variables. So there we only had two variables, and q is always used to denote e to the minus delta, and then we have, in the case of SL2, there is only one more variable, e to the minus alpha 1. Now here you have several more. I mean, there are all these e to the alphas over all positive roots. So for the moment, let's not worry about those. Okay, so let's do the following. Let's again, if you sort of remember each of these terms, so ignoring the first one, this is sort of like what we got in the Jacobi triple product identity. Right? There's 1 minus whatever z q to the n minus 1, and then this is 1 minus z inverse q to the n. Now what I am going to, for the moment, let's remove this asymmetry between this n minus 1 and the n. Let's pull out this term here, which doesn't involve an e to the delta. So what I mean is, let me now just pull out that very first term. If I put n equals 1 here, I get e to the minus alpha. So I'm just going to pull that out. Product alpha in delta naught plus 1 minus e to the minus alpha. Okay, so that's pulled out from here, and remember I'm doing this because I eventually want to get. No, we are not in SL2 dot n. Yeah. I'm sorry, what? There is a what?
Alpha and beta are the same.
Which beta?
Two strings are here. Alpha running over positive, beta running over positive. Two set of positives.
Correct. No, I used the same. No, I just used the same alpha in both terms. That's it. Right? As alpha ranges over the positives, this will range over. The product will range over everything.
Yes. That's also
correct. Okay. So now I'm, like we did back then, I will want to put that z equals 1. Okay, that's the main thing, in order to get some kind of eta function identity. So the idea is to get rid of this z variables, or variables that look like that z part, which is these e to the minus alpha. So we want to get rid of these and only keep q's in the final answer. Right? That's how we got an eta function identity. So I want to remove those. To remove those, I must put them equal to 1, but I can't do that in the very first term because it doesn't come with a q attached. It's only a 1 minus e to the minus alpha. So you remove those alone, and the rest will all have q's. So in fact, the rest look now like this written in terms of q. It's exactly like this Jacobi triple product. 1 minus q to the n goes to the L. 1 minus q to the n now, e to the alpha, 1 minus q to the n, e to the minus alpha. Let's see which term was which. Okay. So that's the product side. I guess that's all that's the best we can do at this point. Now let's look at the sum side of the identity. So I'm sorry, yes? Sorry, I missed that. Yeah, absolutely. There's also a product over. Let's see. So sometimes I write the plus on top and sometimes on the bottom. It just means the positive roots. Okay, so that's the product. Now let's do the sum side. So the sum looks like sum over the while group. Okay, and again the same thing as last time. how do we unravel this? In the case of an affine Lie algebra, we know that the while group is a semi-direct product of the finite while group and that translation. So this is now you write this is the long root lattice, this is a finite while group, and you think of W as just being sigma times the element T alpha of e to the sigma T alpha rho minus rho. Yeah? Is it fine? The sign, okay, correct. Again, as we observed last time, there's only the sign of sigma that you need to take into account. The T alphas are always even elements because T theta was the generator in some sense and T theta was a product of two reflections. Okay, so same, just recall what we did in the case of SL2. So the sign of T alpha is just 1, therefore we only have this. Okay, and we had a formula for how T alpha acts, so let's plug that in. So recall T alpha of rho was by that formula rho plus rho delta alpha minus so rho alpha, then there is a half okay. So that was how that translation acted. Okay, so now all we have to do is really plug this in. Now notice that there is this number which appears when we do this. For example, what is rho delta? Okay, so this coefficient here rho delta, and there is that same rho delta term appearing there. Now in the case of SL2, does anyone remember what we got there when we did the SL2 computation? What was rho delta? It was 2. Right? We did that computation. We said rho is that element which has the property that, at least in the case of SL2, this is 1 for all the simple roots. So, well, at least for SL2. So there it was 0 and 1. It should actually be alpha I checks, but since the norm of alpha I is taken to be 2, alpha I check is the same as alpha I, 2 alpha I over alpha I, alpha I. So therefore this is 1, and delta in the case of SL2, so we said recall by definition delta is always this alpha 0 plus theta 1. In general you will get some number which McDonald's original paper he calls G. This is the number, some number called G, which is, if you look at it, rho alpha naught is 1, right, and by definition, and rho theta would be what we would call the height of theta, because if you write theta as a combination of the simple roots, rho with each simple root gave you a 1, and therefore it's a sum of the coefficients of theta. So this is 1 plus the height of theta, and if we sort of look back on maybe one of the earliest assignments that we had, this is what's called the Coxeter number of that root system. Okay, so notice again I only said things about SL2 or sort of things like SL2. There's a check here, and I'm ignoring the fact that there is a check because I assume that the norms are all 2. So this, what the calculation I did will be perfectly all right if you did it for the root systems A, D and E, where all roots have the same length. If you have different root lengths, then you really have to, the check makes a difference. Okay, so when you do that, you will not quite get the Coxeter number, but something called the dual Coxeter number of the root system. Okay, so anyway, for the moment, just think of it as some number which is somehow related to the height of theta, but there's some number which is fixed once and for all. Once you have the root system, that number G is determined. For SL2, it's 2, for example. Okay, so that's the thing. Let's plug in sigma T alpha rho. I need to act sigma on this guy. So of course it gives me sigma rho minus rho, again you will get plus rho delta, which I am now calling this number g times rho alpha, no, what's this, g times sigma alpha minus, as before observe sigma on delta is just delta, right, delta is left invariant under the while group, therefore it's minus whatever the number was, okay, rho alpha plus half g mod alpha square times delta. Okay. So this is basically what we now have to do, that perform that alternating sum over. So the alternating sum, therefore S, which is this guy. So now I'll swap the order of summation. I'll do the alpha on the outside. So this is now sum over all these alphas in M. So minus 1 to the length of sigma will be on the inside. So the inner sum is the sigma now. So I will collect all those terms which involve only sigma, minus 1 to the length of sigma. Then e to the whatever, the sigma term is only in the first two terms. So I will think of it as e to the sigma of rho plus g alpha minus rho. Okay. So in the inner sum I collected all the terms which involved the sigma and I got this. And the other terms here don't really have sigmas in them. So I can pull them out of the sigma summation and write this as e to the this whole thing. So e to the minus delta times whatever I have there, rho alpha plus half g mod alpha square. Okay. And so again remember our shorthand that q is e to the minus delta. So I will think of this as q raised to this power, but this power can be further, you can complete the square on this term. You can rewrite this quadratic term as follows. I will let's see, what should I pull out, 1 over 2g from here. So it will become g alpha the whole thing square. So I am now trying to complete the square. So I will get a 2g here. So the 2g alpha is done. So I need to add rho. Okay. So I am just doing completion of squares on that term. So if I do that, then this just becomes summation. So that final term which I had is in fact just a constant, only depends on the rho part. Okay, maybe now is the time to make the remark about rho, okay, before I do anything further. Okay, so now let's just for the moment, step back and look at this, this summation here. Let's look at the inner summation. So what does it remind you of? That's the question to ask now. It's a sum over all sigma in some finite while group. It's an alternating sum over the length, e to the rho plus something minus rho, right? That looks like the numerator of the while character formula, right? Okay. And observe here though that rho by definition was the while vector for the big affine Lie algebra, right? It lives on that much bigger n plus or L plus 2 dimensional space. But again, remember if you were to think of this as a numerator of the character formula for the finite while group, you will need rho to be, the half sum of the positive roots or whatever, the vector corresponding to the finite while group. Right. So here's where that remark which I sort of repeated a few times comes into play. It doesn't really matter because all that this detects, when you have sigma rho minus rho, all you need is that rho on alpha I check should be 1 for all the alpha I checks from I equals 1 through L, meaning to say on the finite part. As long as rho performs that function, it doesn't matter that rho lives on a bigger space or whatever else and so on. Just that fact, it's a crucial observation. So you don't really need to worry about that thing anymore. So we might as well, without any problems, do this. Okay, where when I say rho dot, I mean just take, so rho dot is now the while vector or the whatever half sum of the roots for the underlying finite dimensional guy. So this is the while vector So sigma rho minus rho will be the same as sigma rho dot minus rho dot. That's the key observation. So you can as well do that there and thereby make the parallel more complete. This is now exactly the numerator of something that appears in the character formula. But for further consistency, I would want to do that the same rho dot. I don't want to have one row here and a rho dot there. I want to sort of also replace these by rho dots and see what happens. Now here's the question. So where else did I have a row? It was in this term, right? So the question is this: can I replace this by a rho dot, and will that still give me the same answer? Yeah? Why? I need to compute inner product with alpha.
We can make it as 0 on alpha.
What?
X of rho equal to dot plus something.
Right.
That something acts as 0.
Correct. Okay. So the point is, though rho occurs here, it only occurs as in conjunction with an alpha which comes from H naught star. You're only computing inner product of rho with something in H naught star. And so if you think of how rho and rho dot are related, here's what's true. See, rho and rho dot, they both act the same way on the H naught star portion, right? And if you look at it, it will be this plus something involving the lambda naught and the delta. So this plus some linear combination of lambda naught and delta. Okay. So check that this is in fact the case, where the rho is that original wild vector and this is the wild vector of G naught. Right? Okay, so thanks to this, it doesn't really matter here also. I can change this to rho dot. Okay, this is fine. So you need to check that the last thing that I said. And so now we are in good shape. This final expression becomes e to the, let's see, I had a minus rho square by 2g, which of course I can now make rho dot square, of course, everywhere.
Can we choose such a rho? Any rho satisfies?
Good question. Any row should satisfy this. Because see, how is rho defined? It is a row for which it's an element which is 1 on all the alpha I checks, right? Now, if you sort of look at its span, you know, every vector can be written in this way, right? Every vector row in your space can be written as something in the span of, so let me call it rho bar, something which is in the span of the alpha i's and something in the span uniquely. This is a basis after all. All you must check is that this rho dot has the correct inner product with the alpha I checks, right? So that's all you would need to check. So my guess is that anything would do the job. Any row will have to have that property. Okay, so now let's. I'm sorry. Huh? Where?
The delta also is in this linear combination of lambda naught. The delta because there is only alpha naught left. Alpha naught is some k.
No, what do you mean by there's an alpha naught left?
Linear combination of.
Correct.
They, that need not be. The delta term could be anything.
Could be anything. Yes. Correct. Yes. Yeah. I mean, if you want, you can choose it to be 0 for it. Exactly. Yes. But that's a choice. But like what Venkatesh is asking, if you choose any row, it would still, when you look at its restriction to its projection onto the space spanned by these fellows, it should be the row of the underlying finite kind, right? So that's the claim, right? Seems fine, right? I mean, I haven't really checked this, but it looks fine. Okay, so let's just see. E to the minus, what's the extra term? Minus rho dot square by 2g. That's the term on the outside. Now, this now becomes sum over alpha in n. Let's just write this term in terms of q. Q to the, this guy, g alpha plus rho dot square by 2g, some quadratic term, and the term which looks like the numerator of a character. Okay, so it looks like the numerator of some wild character. Let's make it actually look like a wild character. So what would we need to do? We'll have to divide by the denominator, and remember that was exactly that extraneous term on the product side. This was that extra term which you didn't want because you wanted to eventually put a limit there. So that's exactly the term which I isolated. So let's now divide both sides by this term. So I'm now going to look at product divided by this denominator, wild denominator of the finite portion, and that of course would equal this part. So we'll do the same thing on the sum side. So now I look at the sum divided by the wild denominator of the finite portion, and this term I can now think of it as in fact the wild character, okay, and it's got a notation. We usually call it chi for character naught, the finite fellow of this element, right, because that's exactly how the character works, e to the lambda plus rho minus rho over product. So it's the character of that element G alpha, with sort of like highest weight G alpha, okay. So we already have, equating these two things, we have what you might say is, just one step before the eta function identity itself. Eta function is obtained as a certain limit of this identity, but this identity itself is more primordial. It gives you, you can conceivably, and in fact it is very much done, obtain other limits of this identity and get other interesting identities. So this sort of contains, so this is the primordial identity, which is just the wild character formula for the, so let's just say here sort of McDonald identity. So this is the product side without that extra, divided by the wild denominator, equals the sum side, which has now become a nice sum, fine m, there is some quadratic term q to the rho plus g alpha square over 2g times the character of this element G alpha. Yes. This is also a Q. Sorry. Yeah, I missed the delta. There's a delta there. Yes. So that's also a Q. Oh, minus remains.
No. Minus delta is Q. Keep the minus delta is Q. So the minus was.
Oh, sorry. Then I made a mistake here, is it? No. That's right. Sorry. No, there are several minuses. What finally survives? Is this correct?
No, that's a plus. That's a plus.
That looks like a plus.
That looks like a plus.
Because there's a minus there and a minus here. So that's actually a plus. But then the Q is a minus.
Yeah, the Q is a plus.
Okay. Fine. Okay, so that's the McDonald identity, in which we still haven't done any specialization. Okay, but this is just the wild character formula when you unravel what the product side, that is the real roots what the roots look like, positive roots, and the sum side where you unravel the wild group. Okay, so now we are ready to just obtain the limit. So let's put all those E alphas equal to 1 and we'll get our eta function identity. Okay, so corollary, take limit well, I guess I don't need take limit anymore, so put now what exactly does that mean? Right. So at least I'm sort of starting from my right hand side, and I can see that to get an eta function, that is, remember it was just 1 minus q power n, product of that raised to some power. So to do that I need to really get rid of this term and this term. So I'm sort of saying that as take put these guys as 0 as ones, and then of course I will get an eta function identity. Now what exactly does it mean? What does it mean to put these terms equal to 1? Yeah? Okay, so you want to think of these as, you think of this identity in which, so you see these e to the alphas are sort of, they are what? Correct. So in fact you think of this thing as being, so for example the right hand side you can imagine, so it's of course an infinite, it's an infinite, I mean it's a power series in Q, this, in which the coefficients come from the group ring of the underlying root lattice. So this is for example one way of writing this, okay. But what it means is in some sense all these e to the minus alpha 1 till e to the minus alpha L, everything that appears here are some combinations, they are some not polynomial but Laurent polynomial, it can also involve negative powers. So every e alpha term which appears is some Laurent polynomial in these generators, and you set all these generators as 1 in some sense, okay. So in this it would sort of correspond to taking this group ring of the root lattice and just specializing, taking a further homomorphism to Z which sets all these things to 1. Okay, so that's essentially what we are doing. So the right hand side just becomes, so let's see what the right hand side becomes. Becomes product of 1 minus q power n's. The question is how many such terms do you get? Right? Every term is of the form 1 minus q power n, there is surely L of them, and how many more? For every positive root, right, there is a term here, and you think of this as a term corresponding to that negative root, for instance. So there is 1 for each root, or 2 times the number of positive roots. So it is L plus number of roots in the root system, but that's exactly, what's that? The dimension of the Lie algebra. So remember this definition of this Euler product. No, I silently suppress the plus. Yeah, I just put all roots. No, I mean this how it appears there. 2 times the number of positive roots. So it's that Euler product, this one, raised to the dimension of the underlying Lie algebra, because that's just L is the rank, the dimension of the Cartan, and this is the total number of root spaces that you have, right? So in all you get the dimension of the Lie algebra. So that's the right hand side, and so we just need to unravel what the left hand side looks like. Okay, so the left hand side involves, so let's see where are the terms which have alphas in them, which will, I mean E alphas, not alphas. We need to worry about putting those variables E alphas to 1 somehow. So this doesn't have anything, where am I looking? So this doesn't have anything, this doesn't have anything. I mean there's an alpha but no E alphas. It's only here that you have exponentials in the alphas which are going to occur, right? Remember this is just that while character. So it's going to look like this, in which you have some alphas, right? E alphas. So we really have to figure out, in order to figure out what the left hand side is, we have to evaluate, we will have to figure out what you get if when you take this formal character G alpha and you put, so you take these and you somehow set these to 1 here, and the question is what do you get? Yes? Okay, great. It is the dimension of the corresponding representation, right? If you think of this, so for the moment there is just a slight problem, which is that G alpha may not be a dominant root, a dominant weight, right? Remember characters, when you say that this is the character of a representation, the highest weight must be must be a dominant integral weight. Now for the moment let's ignore that. So if it is in fact a dominant integral weight, then this is a character of a representation. So when you write it as a sum of these formal exponentials and putting those exponentials all equal to 1 will only finally give you the dimension of the representation, right? So you can think of this as just put it within quotes, it's the dimension of the corresponding representation. Okay, so sort of use Katz's notation, representation with highest weight G alpha. I am putting it within quotes because it doesn't make sense if it is not a dominant fellow. I'm sorry. I shouldn't do that. Correct. No, but no, not on positive roots. The alphas are not positive roots. I just said it's an element of H star, right? It comes from the long root lattice. Alphas are still elements of H naught star. Right? See the. Huh? No. I'm only thinking of it as an element of H naught star, not as an element of the. See, I'm not using the fact it's a root, but it's an element of the root lattice surely. Right? So it's an element of H naught star is what one is thinking. But you're right. I guess I messed up. I should have been a little more careful here. Let's see. Where should we?
Because it is being written as a linear combination of the visual roots, each goes to 1, therefore the E of that one.
Correct. Yeah, exactly. So, no, I'm just wondering if I can do anything to resolve the confusion in terms of.
I think let it be as it is, because otherwise we'll have to say there put E alpha equal to 1 for this alpha and also for those alpha. You will be putting all of them to be 1 ultimately, not just for the corresponding.
That's correct. Yes. Yeah. Correct. So what I'm really saying is, put these to be 1. Think of it like that. I want to put these to be 1 and then several other things become 1 as a consequence. Right? So all the other E, once I put those to be 1, every exponential will go to 1, which occurs in that thing, not only in the roots. So you're right. Okay, let it be. Okay, so now this is the dimension of the corresponding module, except it may not quite be corresponding to a highest weight representation, but that's not too serious if you sort of look at the Weil dimension formula. So recall, if you were talking about a highest weight representation lambda and you wanted to find its dimension, then so this was what Sendamare had proved. You have lambda plus rho alpha. Let's put rho dot delta naught plus lambda is some, let's say. Okay, so that's the Weil dimension formula for the dimension of this module. Now, if you see how this was derived, right, what did we really use to derive this? All we used was the Weil character formula. So we knew what the character of this module was, and this is in fact the exact procedure that was followed. We took the Weil character formula and then set those exponentials equal to 1. Okay. Now, when you do that, the Weil character formula, the numerator is an alternating sum. The denominator has things of the form 1 minus an exponential. So when you set those exponentials to 1, the limit will become the form 0 over 0 if you attempt to do that, right? And so what you do is use L'Hopital's rule, which is basically what is that, is behind that proof of the derivation of the Weil dimension formula. So how do you get Weil dimension formula from Weil character formula? Well, you use a souped up version of L'Hopital's rule, because when you attempt to put the limit directly, it becomes 0 over 0. Okay, and so to do that, you must use those derivations. So what you do is, the usual trick of L'Hopital, you take derivative of top and bottom, and then you try to put the limit. Okay, and those were those derivations. Here it's a function of many variables, so you must sort of use appropriate derivations, right? Those were those derivations which, in fact, Sendamare had defined in class. So it's just sort of you use L'Hopital's rule, and then you see what the limit becomes, and it turns out to give you exactly this thing. And that proof never used the fact that lambda is a dominant weight. Okay, so if you go back and see, it was just a purely formal exercise. This limit, this quantity over that, attempt to see what you get by L'Hopital's rule. So you do in fact get the exact same thing if you attempted. Okay, no, let me not erase this. So I guess what I'm finally driving at is, you take the formal character. Okay, instead of lambda, you put anything you want, and you try and take this limit. Okay, and you do it by L'Hopital's rule. The final answer will be exactly what you got, because that was exactly the derivation of this dimension formula. Okay, so Yes. So my claim is that when you take chi naught G alpha and you try and put all those E alphas to 1, the answer is exactly what we will call D0 of G alpha, which is just this product G alpha plus rho. Okay, I shouldn't use alpha here, beta So it's sort of the same thing given by the wild dimension formula, except it may not be a positive number anymore. If you did it for a dominant weight, you will get a positive number. If you take any arbitrary fellow and attempt to find it, the answer is still correct, that's the limit, but sometimes it's 0, sometimes it's a negative number and so on. Okay. So but anyway, there is this well defined quantity that you can compute, and so the left hand side now becomes, when you specialize, when you set this limit, it becomes q to the minus rho square over 2g sum for all alpha and m. So instead of that chi 0, it becomes the corresponding wild dimension d0 of that element. So some number, positive, negative or 0, integral times the norm of that vector q raised to Okay. So these two things are equal. That's again sort of almost the eta function identity, but I've got an identity for the phi function. Phi q raised to the dimension is equal to whatever I have on this side. Okay. So it's almost done. So here's sort of the, like I said, the one final surprise. So there is this extra term which is on the outside. So I have LHS equals RHS. Now I have this power of q which is sort of right here, and it's just some quantity. If I ignore it, it's a nice looking series with integral coefficients. Here's an extra power of q, and we actually know what that number is. Okay, so this power of q which appears here turns out to be this. Okay, 24 again, but this is what's called the strange formula of Freudenthal. This is the same Freudenthal whose formula we had seen before, and de Vries. Okay, so here's something called the strange formula, which computes the norm of the Weil vector. So if you have, and remember, all this is with respect to, this norm that one is computing is with respect to the normalized invariant form. Meaning to say this, when you're computing the norm, you should know what form you're using, right? So you're using the form which is, with respect to which the long root has norm 2, right? Theta theta equals 2 was the normalization we used. If you take that form and if you compute the norm of the Weil vector divided by 2 times this number g, right, rho delta, or the dual Coxeter number, it turns out to be the dimension of g over 24. Okay, so that's one thing to keep in mind. Now I will add another, but this is already sufficient to derive our eta function identity. So now what do? Well, we just push that power of q to the other side. So the final corollary says that you look at q to the 1 over 24 phi q raised to the dimension of g. That's nothing but the sum all alpha in M, this number times q to the and remember this q to the 1 over 24 phi q is what we had called the Dedekind's eta function. So, this function here is exactly what is called the Dedekind's eta. So, let us write it as eta of q. For our purposes, you can think of it as a power series in q to the 1 over 24, and I mean this had the nice property that if you raise it to the power 24, it ended up giving you this Ramanujan's function, which is q times the product 1 minus q to the n to the 24, and which is which is a modular form. It has nice properties. Dedekind's eta function itself, if instead of the formal point of view you think of q as e to the 2 pi I tau and so on, it's a nice function on the upper half plane. So, in fact, a modular form has lots of nice properties. So, this this strange formula miraculously ends up giving you this q to the 1 over 24. Naturally it just pops out of this. So, that's well, that's what one calls the McDonald eta function identities. So, what it gives you is an identity for a power of the eta function corresponding to the dimensions of every one of the simple Lie algebras. Okay. So, if you unravel the right hand side, what you would get would be an identity, and we have already seen examples of this before. If you take the algebra to be SL2, it gives you an identity for the third power of the eta function, which is what is called the Jacobi's. This is due to Jacobi. If you take G to be SO5, which is the B2 root system, then it gives you an identity for the 10th power of the eta function, which is what was called Winquist's identity, which he used to prove the remaining of the Ramanujan congruences. And if you take G to be SL4, then SL5, which is A4, then it gives you a thing for the 24th power of the eta function. Therefore, it gives you an identity for that Ramanujan function itself, and this was the corresponding formula was the thing which I said was found by Dyson. This called the Dyson's identity. Okay, so you actually get one for several powers of eta function. Okay, so that is that's more or less it. That's more or less the main identity. But I also wanted to say one more thing. If you look at what the right hand side looks like, okay, so it's some integer linear combinations of certain powers of q which are quadratic functions. So if you see what this thing really represents, alpha is running over some lattice, okay, M, and M is sitting inside the this is the lattice spanned by the long roots sitting inside H naught star. So if you sort of restrict only to the real span of the roots and so on, the form on H naught star is positive definite. So there's a nice positive definite form, the killing form, for example, on H naught star, and you're taking some normalized version of it, and you're looking at a certain lattice inside that space, which is the lattice M, and you're translating that lattice by some element. Okay, rho naught is some element in this space, and you are translating the lattice. So it's a translate of a lattice, and you are counting the norms of the lattice points. Okay, so this is the generating function for the norms of lattice points. So this is sort of the kind of thing that appears in what are called theta functions. So this is a natural thing to consider. Here there is also a weighting factor which tends to be plus or minus and so on. If you didn't quite have this, then this is sort of like a what one would call a theta function. Now that factor g which appears here on this norm square and so on. So here's the second thing I wanted to say, which is the following. Observe there are actually two different forms on H naught star. So there are two forms. There exists the killing form, So, when we were doing all these, the forms and so on, so what we are using throughout is the normalized form, right? But we know that all forms are just multiples of each other, right? If you are taking a simple Lie algebra, then all these invariant forms are just some scalar multiples of each other. So, here we have some normalized form, but of course, remember the canonical fellow is the killing form, right? So, and remember, how did the killing form arise? It first lives on H naught. Its trace of add x add y, right, lives on H naught, turns out to be non-degenerate. You use that to push it forward to get a form on H naught star, right. So, that is what I mean here. There is a killing form on H naught star, and of course, there is this normalized invariant form. Okay. So, you can always ask the question, how are these two things related? They must be some scalar multiples of each other, right. So, this form that I am using to compute norm of rho square. So, the question is, how are these two things related? Right? That is something that one would certainly want to know, and it turns out that is exactly the answer. Okay. So, this factor, which seems somewhat strange at this point, 1 over 2g, is in fact exactly what you need to scale the killing form by to get the normalized form, or the normalized form, you divide the normalized form by that in order to get the killing form. Okay. Okay. And I mean, you can sort of see this if you are doing it in the case of SL2. So maybe I should just think of SL2. There are these fellows HXY, and you would really do the following. If you think of what is trace of add x add y, the killing form of H with itself. So, the killing form is you pick up lots of extra coefficients. I mean, for example, it's too big a calculation. Add x add y. So, it is acting on this 3-dimensional space. Add x has eigenvalues 2 and minus 2. So, if you try to compute this, trace of add x add y would be, anyone remember? Add x, add h, I am computing trace of add h square. 4. So, the two eigenvalues are 2 and minus 2. So, I have to take squares of both of them. 4 plus 4 is 8. Okay. So, it's always very large. You will get a larger number than what you expect typically. So, the killing form H with itself is 8, whereas the normalized invariant form, so remember all this should actually be in H star, but at the moment I am doing it in H. So, imagine if you are trying to do a normalized invariant form in H, this is what you would pick, right. H is sort of the analog of the highest root. So, you would make it 2, and so notice it is off by a factor of 4, okay. And G, as we saw last time, was 2, right. So, it is off precisely by the factor 2G, okay. And here I am doing it in H rather than H star. So, the killing form will be larger than the normalized form. If you push it to H star, the thing reverses. The killing form becomes smaller than the normalized form. Okay. So, there is some duality at work, but otherwise you can sort of see it in action right there. Okay. So, this is the next thing which makes it possible to even recast this further in terms of the killing form. So, if you wanted to rewrite this further, you could say this is nothing but okay. So, in fact, call it m dash, which is you scale the lattice by this factor m, okay, because notice it is only g alphas which appear everywhere. So, I look at this sort of the coarser lattice g times m, and this is now g dot d dot of this number beta q raised to killing form of just another equivalent version of the McDonald eta function identities. And again notice we had that more primordial identity that I had can actually be used to get lots more by way of identities. So, observe, for example, the Euler's pentagonal number theorem, which was the thing for eta to the 1, it was a formula for just eta itself, that does not appear as part of this list, okay. And if you remember one of the proofs that we gave from Jacobi's identity, it was deduced, right, by substituting q and z to be something or the other and so on. And so there's sort of a more natural thing you can do. You can take that unspecialized McDonald identity, so one step before this, don't put the limit yet, and take that and sort of put a different limit. So you sort of look at some degree, order 3 automorphism of SL3, and you do something further, and instead of getting these numbers, you get slightly different numbers. This dimension is sort of like the trace of the identity map. Instead, you will get trace of other operators and so on. So whatever. So you get a different identity by specializing differently. Okay. So that's one other thing to keep in mind. Okay. So let's see. Now, one thing I wanted to say about this strange formula itself is, this is actually let's see. There's a sort of a baby version of this strange formula. There are several strange formulas in this business, but here's one more, for example, which is if you take the product over all positive roots of theta plus rho alpha over rho alpha, okay, then what do you expect to get? Theta is the longest root, the highest root. Yeah? Dimension of G. Right? Because this is the wild dimension formula for the adjoint representation. The adjoint representation has highest weight theta, and so the dimension of the Lie algebra is actually given by this formula. Right? So observe the dimension of the Lie algebra often, so this is sort of the baby version of this strange formula. This is, you can think of this as the 0th order version, and there are sort of these higher order, at least there is one other formula, it's some kind of higher order correction to this formula here. Okay. And you can actually check this explicitly, for example, in the case of SLN. Okay, it's very easy to see that in fact this number is exactly dimension G over 24. So I've seen Freudenthal's original proof, which is sort of behind this remark I made. See, the wild dimension formula that you have is the 0th order for what's called, so you can actually get a finer version of the dimension formula, okay, which is you not only look at you look at what's called the principal specialization, okay, something that I'm going to sort of say a little bit more about, but you actually get a finer version of this dimension formula, in which if you see what you get at, so it depends on a variable q, sort of a graded version of it. When you put q equals 1, it just counts the full dimension, and that's this dimension formula. If instead of q equals 1, you sort of expand it in Taylor series, and you see what sort of the next power of q minus 1, okay, and then it turns out that has to be 0, and this identity just says that the next term in the Taylor series is 0, for example. So that's how Freudenthal proves this formula. But I think there are several proofs since. Okay, so I sort of just wanted to make a few more remarks about this thing called principal specializations, which is, again, since it's after all related to this whole business of So the idea itself is very simple. If you have a representation of G, which, for example, just imagine you're talking about a finite dimensional Lie algebra, even a finite dimensional simple Lie algebra, and you want to understand some irreducible highest weight representation of G. So we know that there exists some highest weight lambda, right? And the entire representation is sort of everything lives below lambda. So in some sense, all the weights in the representation are below lambda, right? That's what highest weight means. So, and of course, there are several weights all over the place, and each weight corresponds to some weight space. So, your representation, let me use again the terminology L lambda for the highest weight representation. It breaks down into weight spaces. Mu belongs to, say, lambda, and you want to understand. So, trying to understand the dimension of this representation L lambda is just you want to sum up all these dimensions of these fellows. Right? Add all their dimensions up of the weight spaces, and that's the total dimension. But that's a very gross information in some sense. So, here somewhat finer information, since you know after all that every weight is of the form. So, all weights are smaller than lambda. So, each weight is of the form lambda minus a linear combination of the simple roots. Let us say there are n roots. So, every mu has this form, right. So, you define the depth sort of like height. Let us call the depth of mu as the sum of these coefficients. Okay. So, for example, the only weight at depth 0 is lambda itself. This is the depth 0 weight. Now, depth 1 would be anything which looks like lambda minus a simple root. So, maybe there are several of them. Like maybe there is a bunch of depth 1 roots. So, these are all roots at depth 1. So, it is depth 0, depth 1. So, you look at things which are at depth 2, depth 3 and so on. So, you sort of just stratify your module in this way. You just keep track of how many you get at each depth, right. So, that is one, it is slightly finer information. So, the finest information is the character itself, because it tells you how much is there in each precise weight space. That is the wild character formula, right. So, that is the finest information you can get about your module. But if you want to make do with somewhat less fine information, here is one you can do. You can look at how many there are in each depth. Okay. So, that formula that you get, I mean the resulting thing is what is called the principal specialization. So, here is a definition. So, let us give it some name. F L lambda is the principal specialization of L lambda, depending on some variable, I will not call it Q. U is defined as summation over all weights mu which occur, dimension of this weight space, Q to the depth of mu. Okay. Here depth depends on what lambda I have fixed. Okay. But assuming I fix some lambda once and for all, this is the generating series for, this is what you would call the principal specialization of that module L lambda. Okay. And if you see what does the coefficient of Q to the n tell you? It's a number of, it's the total dimensions of weight spaces which are at depth n, right. So, that is the generating function for the weight spaces at depth n. This is fine, definition is okay. Okay. So, now here is the interesting thing, after all the character, the wild character formula contains the complete information about the module. So, you should be able to extract information about the principal specialization just from the wild character formula itself. So, you are after all looking to get something grosser information from the finer one. So, here is the proposition which says if you want to find the principal specialization, yes?
That should be Q, instead of U.
Yes. No, what? U, right? No, I changed it for a reason actually. Yes, because there is already a Q when I go into the affines, and I am certain to confuse myself. So, okay, so that is the, okay, then maybe we shouldn't call these mu's, they look too much like the u's, gamma. Let's make it gamma. Depth sub lambda, okay. Okay. So here's the proposition. You can actually compute this principal specialization from the wild character formula. Okay. So maybe I should say I should actually put checks there, but I'm going to just assume, for example, that I'm only talking about one of the simply laced ones, A, D, E. So that all roots are the same length. If you didn't want to do that, you will actually have to put checks. So maybe I can state it in general. So maybe let's just say you take everything, but okay, so it's a pairing. So that's a formula for the principal specialization. Okay, and as you can see, it looks very much like the wild dimension formula itself. The exponents of u that appear are exactly like those that appear in the wild dimension formula. And in fact, if you now want to set u tending to 1, right? So how, for example, if you prove this, you can prove the wild dimension formula from this by letting u tend to 1, because if we apply L'Hopital's rule to the top and bottom, right, you will exactly get the exponent of u here and the exponent of u there, and that's exactly the wild dimension formula. Okay. So this is somewhat finer information than just the dimension itself, and the proof is not hard. It's just you just take the wild character formula and you just try and figure out what depth really means. And if you see what depth means, depth is just this. Okay, that's the reason why this works. Finding the depth of something is equivalent to taking lambda minus mu and finding its inner product with the element rho. Okay, this is again I'm assuming simply laced here. If not, there were checks, and then I need to worry about it a little bit. Okay, I'll need to put a check. So anyway, you just apply this and you will find that this pops up. So that's the principal specialization, and in fact the exact same formula will work even if your Lie algebra is not. So this is, of course, here it could be any Lie algebra, so it can be finite dimensional or affine. So let's remove that. Where, of course, if you are also talking about the affine, we should do that. Okay, so this takes care of both cases, whether you are talking about finite or affine. You still have the same sort of notion of what this principal specialization needs to be. Okay, so right. Okay, that's the problem when you are in the affine. It just means you take the roots of the dual Kac-Moody algebra. So if it's simply laced, then there is no problem. You will just convert this into inner product and be done with it. But if not, you must take the roots of the dual affine. So there is no one-to-one correspondence, there is no natural correspondence between the roots of the original and the dual affine. That's what. So it's not, see this, so technically I should say overall alpha check running over this. That should be the correct way of saying it. It's not over alpha running and then you are taking alpha check. You are actually running over the roots of the dual affine. That's you are right. Yes. Because there is no correspondence between the two in the affines. Okay. Okay. So anyway, so you have this principal specialization, and so like I said, this multiplicity of alpha check now, I guess, but it will turn out to be the same. Okay, yeah, actually it doesn't make sense if I write it that way. Yes. And so the strange formula, for example, so I mean this is all rather just souped up versions. If you just prefer to think of it in the finite dimensional situation, that's perfectly fine. And the Freudenthal's formula, the strange formula, is what you get if you think of this and expand it in powers of u, for example. So when you put u equals 1, it gives you the first term in the Taylor series is the dimension, right? Now when you look at to expand in powers of u minus 1, sort of, I guess the first u minus 1 itself vanishes. U minus 1 square is what gives you that strange formula applied to the adjoint representation. I should say that also. So this was at least Freudenthal's original proof. Okay, so that's about this. Let me just see what else I want to say. So just a few more remarks about the structure of these highest weight representations when G is affine. Yes? McDonald eta function identities is only the study of the trivial representation and what the corresponding identity is, right? But then we want to understand how these general integrable representations, which are highest weight, integrable highest weight representations. So we want to understand these representations L lambda, where G is an affine, where lambda is an element of the dominant integral weights, right? And one wants to understand, for example, the structure of what weights appear and so on. So recall in the finite dimensional case, so we have lambda, and so what are the weights in the finite dimensional case? Suppose we wanted to, so sort of in Shuklaji's notation, it's P of V, where V is now the module L lambda. This is just the set of weights for that module L lambda. So this is all mu's such that corresponding weight space is non-zero, right? So question is, how does one figure out what these are in the finite dimensional case? Given a highest weight lambda, what are the other weights which appear? Well, the situation in the finite dimensional case is that you just have to look for, so let's see, so proposition, at least if G is finite dimensional, so let's state it for G dot, so finite dimensional simply algebra, then the set of weights of this highest weight representation. So one uses this facts about how the Weil group acts and so on. So we know that there is this so-called dominant Weil chamber, and all weights, given any weight, it's conjugate to something in the dominant Weil chamber. So and we also know that these representations are, the weight spaces, the multiplicities of weight spaces are invariant under the Weil group. So if L lambda mu occurs, then so does L lambda sigma mu for every conjugate of mu. So it's enough to somehow understand which weights lie in the dominant chamber, because then from those, by Weil conjugation, you can get all of the roots. So it's really enough to understand what one would call P plus of L lambda, which is only those dominant guys. So P plus is just lambda plus intersected with these weights. And in the case of the finite, this is actually very easy to describe. Okay, that's just a very simple characterization of when something is a weight in the finite dimensional case. It's just all things, all dominant elements which are less than or equal to lambda, where less than or equal to is with respect to that, the usual partial order. Their difference must be a positive or non-negative combination of roots. Now, it turns out that the same thing is true if one is looking at an affine Lie algebra. So the exact same thing is true. So G is a finite dimensional simple Lie algebra, or G affine, except here you need to make, if you are doing it for the affines, you just need to rule out the trivial weight. So except when lambda is 0. Okay, so this is true. So I should say G affine, and let's say lambda is not 0. Then the very same thing remains true. Okay, So except for the trivial module, as long as that central element acts non-trivially on your representation, then you will always get the exact same thing. You just need to understand the weights which are smaller than or equal to lambda. Okay. So that's one nice thing, and I'm sort of lying a little bit here. Again, like I said the other day, there's a delta also which you can have, okay, zeros or deltas and so on. But adding delta never makes any difference. So let's ignore that for the moment. So therefore, trying to understand the structure of these root spaces, or I mean weight spaces, in the case of these affine Lie algebras, boils down to trying to enumerate that set. So given an element, so here's sort of the most standard example. You would start with the highest weight representation with highest weight lambda naught, and you try and figure out what are all the weights that can appear in that representation. So you want to understand what weights appear in this representation. And as we said, it's enough to really understand the dominant weights. So this would mean look for all mu's which are dominant, which are less than or equal to this guy. Okay, so that's the first step. And so the nice thing which happens here is, you know, once you know these, the rest can, as usual, be obtained as just wild conjugates of these fellows. But imaginary? No, what's your question? It's not true in the infinite dimensional case, but the weights which appear are certainly closed under the action of the while group, right? If mu is an element, is a weight, then so is W mu. So therefore it's still okay. You just need to look for the weights which are. So I'm not saying that every element of H star or every weight will be in a conjugate of the thing, but the ones which appear, which can possibly appear as weights of modules L lambda, will surely be conjugate to something. That's the thing. So the fact here is, at least for L lambda naught, it's rather easy to describe. So I guess these are just a collection of facts about L lambda naught that I just started talking about yesterday. The fact is, you can actually figure out what these things are rather easily. Is just all things of the form lambda naught minus n delta, okay, where n is greater than or equal to 0. So in other words, this says to understand this representation L lambda naught, so this picture of L lambda naught, so there is lambda naught itself, and then there is this line through it. So there is lambda naught minus delta minus 2 delta and so on. So you have this string of weights, and these are the only dominant weights which appear in this representation. Okay, so these are the only possible dominant weights which can appear in this representation, and all other weights which appear are therefore just wild conjugates of these weights. Okay, so if we now want to know what are all weights which appear, all you'll have to do is just compute wild conjugates of all these fellows. Okay. So which means, so this is W acting on lambda naught minus n delta, but observe W delta is delta. Delta is again preserved, right? It's a special element. So in fact, this is nothing but W lambda naught minus n delta itself. Okay. So in other words, because of this very special nature of the dominant weights of this module, it's easy to figure out what all the weights are. You just look for what is the while orbit of lambda naught. Let's say these are all the elements in the while orbit of lambda naught. You take those and you subtract them by delta, 2 delta and so on. So you just subtract delta from each of those, and what you end up getting is this whole module. Okay, so it's sort of just these two separate directions. You figure out what the while orbits are, and on the other hand you see what the dominant weights are. So, between these two you can reconstruct the whole module, and along, so the multiplicities of weights are constant along the orbits, right, just by the usual property that if something has a multiplicity, every while orbit element has the same multiplicity. So, it is constant along these directions. So, the only thing you will need to figure out is how the multiplicity varies along this transverse direction. So, if you figure out what the dimensions of those weight spaces are, then you can reconstruct the, get some picture of what this whole module looks like. Okay, so this is very special. What I am saying is all very special for lambda naught. And it turns out, so I guess we'll stop with this final theorem statement. Which sort of explicitly says what this is. And again, it's probably special for A, D, and E. So let G be an affine of type ADE, meaning say all roots have same length. Then these multiplicities, then the dimension, for example, okay, so and I should say rank and dimension of the underlying Cartan subalgebra is L and so on, all the usual data. Then the dimension of these weight spaces as a function of n, how do they vary is the question. So, to understand this, as usual, it's always best to form the corresponding generating series, right. So, in all, you'll see this as a standard pattern in anything related with affine algebras. You never want to study individual numbers. You always see what happens in the entire delta string through that number. So, instead of studying each of these, you just form the generating series and you ask, oh, do I know anything about that? Okay. So, then this generating series turns out to be raised to the n. Okay. So, it is sort of the eta function or the phi product to the minus L. Okay. So, it is something to do with the negative powers of that function, but if you sort of interpret, or if you remember, if L is 1, for example, these coefficients in this expansion are just the number of partitions of n, right, the product of 1 minus q to the n. So, is one of the examples we had. If you ignore this, then you expand this in power series, the coefficient of q to the n is p of n, the number of partitions. And so, this is sometimes what is called the number of partitions into L colors. You also imagine there are L colors of partitions. And then when you see how you can partition something, then those numbers you get are these. Okay. So, anyway, so that's sort of the, that's again one of the nice results, and something that can be proved using this business of principal specializations. But okay, I guess I don't have too much time to worry about that. So, maybe I will just stop here.